Good afternoon, class. So these video notes are going to be over exponential functions. So an exponential function is just any function of the form f of x equals b to the x, where b is greater than 0 and b does not equal 1. Now the reason this is true is that, well, if b equals 1, right, and we just have 1 to the x, then every time we multiply 1 by itself, we're just going to end up with 1. So we're not going to worry about when b is equal to 1. And b has to be greater than 0, because if b is a negative number, then when we take, like, if we had negative 1, right, to the 1/2, right, let's say x is equal to 1/2, then this is an imaginary number, and so this function wouldn't be defined at that point. Now, notice in these functions that x is actually, the variable is an exponent. So the variable is an exponent. And what this means is that your x number is just determining how many times you multiply by b, right? So if x is equal to 2 or x is equal to 3, that's how many times you're multiplying the number by b. So the domain for these functions is just what our x values are. For these, because our x is an exponent, we can have any number there. X can be negative, x can be 0. If x is 0, then obviously the exponent, b raised to the 0 power is always going to be 1. And x can be any positive number. So we just say that x can be all real numbers. Our range for these functions, it's going to be our y values, right? And for these, there's no amount of times, even if b is like 0.1. Like if b was 0.1, even if we multiplied it by itself 1,000,000 times, it would never quite reach 0, right? So our range is going to be basically just all the y values that are greater than 0, because there's no way for our function to ever hit 0. And because of that, that means we have an asymptote at y equals 0, right? And an asymptote is just a line that our function can't cross. So we have kind of two different forms that this function takes. One of them is when b is greater than 0. And so some examples of this are going to be like when b is, you have like 2 to the x, maybe 3 to the x, so on and so forth, where you're multiplying whatever you had previously by 2 or 3 and you're growing. And so we call this exponential growth. Exponential growth. And the graph of these functions looks something like this, where you start low and then it increases very quickly. For b between 0 and 1, an example of this would be like 1/2 raised to the x, maybe 1/3 raised to the x. Maybe you've seen this one, like 1 minus 0.5 raised to the x, something like that, where it's a number that's going to be less than 1 that you're multiplying each time. And for that one, we call this exponential decay, because we're shrinking, right? If I'm multiplying by 1/2 each time, then I'm shrinking the value each time. So we call this exponential decay. So decay. Great. And then the function kind of looks like this, where we start high. That's a bad graph. We start high and then kind of come down low. And this does cross the axis. As opposed to our growth, where we start low and end high, we start high, then low, because we're decaying. And so we want to think about maybe how is exponential growth and decay different from linear increase and decrease. Well, in a linear graph, we have like y equals mx right? Where we have like the slope and then our x value. And so really we just add m, right, for each x. Right, so every time we go up by 1x, we really add m to whatever the value was. With exponents, exponential, where we have y equals maybe b raised to the x, we multiply by b each time. So whereas linear graphs are kind of characterized by adding a constant value each time, exponential graphs are characterized by multiplying by a number each time. So exponential functions can be used to model a lot of situations that have a constant percent of increase or decrease over time. And usually the formula we use for these looks like this, which we read as a of t equals a naught, which is just the naught just refers to this 0, times 1 plus or minus r to the t. And this plus or minus just refers to whether we're dealing with exponential growth or exponential decay. And we'll talk about that in a second. But as I said, a of t just refers to our amount after time t. And then our t just stands for time. So this can be months, this can be years, this can be minutes, it just depends. A naught is just our initial amount. So it's the initial amount. Sometimes we call this the principal if we're talking about interest. And it's just whatever we started with. And then our R is just, if it's plus, it's our rate of growth, or our growth rate. Say it's our growth rate. And if it's minus, then it's a decay rate, right? Because if it's minus, then we get a number that's less than 1 here. And so we have a decay happening. So very practically, let's just look at a couple examples. So the population of Faketown, Iowa was 1,234 in 1990. The population increased by 2.6 per year. What is the population in 2016? Well, we're just going to kind of list out all our variables in this equation. So we're trying to use the a of t, right, equals a naught times 1 plus or minus r to the t. And we can know that this is going to actually be plus because it says increase, right? Increase means plus, right? We're adding to it each time. We know that our A naught is just our initial amount. So it says that the population was 1, 2, 3, 4. So we start with 1,234. And then we know that our rate is going to be 2.6%. We always want to write our rate in a decimal though, as a decimal. So this is really 0.026. And then our time is going to be wherever we end, right? So 2016 minus what we started with. So we started at 1990 and then we are ending at 2016. So if you subtract 2016 from, or 1990 from 2016, we get 26 years. And now we have all the parts that we need to solve for A of 26. So we set this up as saying, well, we want A 26. We know that that's equal to 1,234 times 1 plus 0.026 raised to the 26th power. And this will give us about 2,405. Okay, so in this problem we have 400 milligrams of ibuprofen. And it says that after 6 hours, we have 51 milligrams of ibuprofen remaining in his system. So we started with 400 and we ended up with 51. So that tells us that we're going to be dealing with decay. So we're going to be using the 1 minus r with whatever our r is going to be. how much ibuprofen will be left in the system after 8 hours. So in this one, at the end, we want to know what A of 8 is. Here, though, we know that our A naught is going to be 400, right? Because that's what we started with, 400 milligrams of ibuprofen. But we have a problem in that we don't know what our rate is. So we have to figure out our rate using the information that's been given to us. What we do know is that A of 6 is going to be 51. But that's also equal to 400 times 1 minus r raised to the 6, right? And so if we do some algebra, we can divide by 400, and then get that 51 over 400 equals 1 minus r to the 6. And then we can take both sides and raise them to the 1/6 power so that we will end up getting 51 over 400 to 1/6 equals 1 minus r. Now if we put this in our calculator, we get 51 divided by 400, all raised to the 1 divided by 6. This gives us about 0.709 equals 1 minus r. So if you subtract 1 by both sides, we will get negative 0.29 about. And that equals our r, our negative r. But now we need to multiply by a -1 in order to get our actual r. So we need to multiply both sides by -1. 1 times this, which gives us that our r is really equal to 0.29. So now that we have our r, and we have our initial value, we can finally go back and calculate what A of 8 is going to be. So A of 8 is just equal to 400 times 1 minus 0.29, all raised to the 8th power. So if you just plug that into your calculator, 400 times 1 minus 0.29, all raised to the 8th, gives us about 25.83 milligrams left in his system after 8 hours. So for this problem, what we had to do was we first had to find the rate because our rate was missing, and then we had to use the rate to solve what we were initially being asked for.